potassium permanganate is a deep purple ionic solid which has many uses as an oxidizing agent. It is readily soluble in water. At the surface of the ionic solid, molecules of solvent interact with the potassium and permanganate ions. The positive hydrogen N is oriented toward the permanganate ions, while the negative oxygen N of the water dipole is oriented toward the positively charged potassium ions. As the ions interact with water molecules, they are drawn from the surface, surrounded by solvent, and move independently.
Hi, welcome to Chapter 6. This chapter covers solution chemistry. That video that you just observed is the dissolving process when ionic substance goes into water. What happens is that the ions in the ionic substance, like sodium chloride, will orientate themselves so that the water molecules can either connect through the hydrogen or the oxygen, depending on whether it's attracted to the chloride. Negative chloride will be, of course, attracted to the positive hydrogen, and the positive sodium will be attracted to the negative oxygen in water, and then it causes them to break apart in the lattice of the salt. We'll see that more in today's discussion. This is a video of how water dissolves salt. You can see that the water molecule orientates itself to the positive or negative ions. Here you see the hydrogens in red and the oxygen in blue. The hydrogens are positively charged, the oxygen's negative, and then you have the ionic substance, sodium chloride. Sodium's positive, chloride's negative. And you can see here where opposite attracts. It takes more than one water molecule to dislodge the ions. And when you put salt in water, that's what happened at the molecular level. Here, water molecules pulls the sodium chloride away from the ions. So, when you put salt in water and it's clear, what we have is a solution. What is a solution? Well, solution is a homogeneous mixture. You know it's homogeneous because the consistency is uniform throughout. When the consistency is inconsistent, then that's a heterogeneous solution. Solution contains two or more substances that are mixed in uniform consistency. The components of a solution are the solute, which is generally the minor component, and it's the component that is being dissolved, and the solvent, which generally is the major component and which dissolves the solute. If the solvent is water, then the solution is called an aqueous solution. Here, what you see is a solution being prepared. The blue powder on the scale is copper sulfate, and that's a solute. Generally, to prepare a fixed amount of solution, you weigh that amount of solute, then you put it in this container called a volumetric flask, and then you fill the volumetric flask with water. You shake it up so that the mixture is uniform, and then you fill to a specific volume. Now, if you know the mass and you know the volume, you can actually calculate the concentration of the solution, which we will see later in this particular chapter. So, what type of solutions are there? Well, the solution is dependent on the solute. Remember, that's a component that's being dissolved, and the solvent, which is the component that does the dissolving. Together they form the solution. And because we have three phases of matter, solid, gas, and phase, then generally you have 9 types of solution. You can have a gas in a gas. An example of that is air. Air is nothing more than a mixture of gas. And if you try to look at air, which you can't see, so it's pretty uniform, then what we have there is a solution. Pollution, however, is not a homogeneous solution. Gas in a liquid, that's carbonated water. Gas in a solid, that's whipped cream or foam. When you have a liquid in a gas, that's an example of a fog solution. If you have a liquid in a liquid, then an alcoholic beverage like wine might be the solution. If you have a liquid in a solid, then that might be dental amalgam, like the mercury in silver. Then you can have a solid in a solid, in which case you have, say, a mixture of gold. 14 karat gold is actually a mixture of gold and some other metal. If you have 24 karat gold, then that's pure gold. And then you have a solid in a liquid, and the classic example of that is salt water or sugar water. So what are the characteristics of a solution? Well, you know how you have a solution because the particles at the molecular level is uniform throughout that mixture. So what you have is, here's an example of a solid in a liquid, and it has uniform consistency. And what makes a solution really a solution is that it's transparent throughout. Also, it does not separate upon standing. Like that example, that's not a true solution because what you see is it's cloudy and there's separation there. That's a heterogeneous mixture. The components can be separated by filtration, cannot be separated by filtration, but it can be separated by an example like distillation. The solute and the solvent mix in ratios up to the solubility limit. Solution is almost always transparent. And I said earlier, it can be separated by other means like distillation or chromatography. So, when you have a liquid in a liquid, then what we have is something called a saturated or supersaturated or unsaturated solution. And an example of that is the following. Actually, this is true for not only liquid and liquid, but also solid and liquid. For example, if you take a pinch of salt and you put it in a glass of water, you'll see that that pinch of salt disappears. You can add more salt, in which case that solution is called an unsaturated solution because the mixture can actually hold more of the solute. More of the solute can dissolve. Now, if you keep adding salt, you get to a point where you've saturated the solution. You can't add any more without the solute dissolving. Take, for example, if you're in a classroom and there are 48 seats. Well, saturation is when you have 48 students in those 48 seats. That's called saturation. If you have more students than seats, then you have supersaturation. If you have less students than seats, then you have unsaturation. So that's an example of how you can visualize unsaturated, saturated, and supersaturated. Supersaturated, the solute are actually dissolved, but it's past its solubility limit. And I'll show you an example of a solution that is supersaturated shortly. Now, when you have a liquid in a liquid, then the term is miscible and immiscible. And this is only the terms you use when you have a liquid solute in a liquid solvent. For example, alcohol and water, or oil and water. So when you have two liquids that are soluble in each other, alcohol and water, for example, you have a miscible solution. When you put oil and water, on the other hand, it separates. Why? Because the two liquids or the two components are different from each other at the atomic level. Here's an example of a supersaturated solution. What you see here is a top view of a petri dish, and what you see is the solution that is supersaturated. Next, you will see that you take a pinch of the solute and drop it into this petri dish, and because it's supersaturated, it automatically crystallizes. And there you see the crystallization because the solution is supersaturated. This is like making rock candy, for example. In this case, this chemical is called sodium acetate. So what is involved in the dissolving process? Why do certain substances dissolve in each other and other substances do not? Well, let's take a look at the solubility factor. So the characteristics of the solute and the solvent are important. In an aqueous solution, water is a solvent, as I told you earlier, and it generally will dissolve polar molecules. Polar molecules are molecules that have positive and negative ends. And the reason why polar molecules will dissolve is because water is also polar. On the other hand, if you try to dissolve oil, which is a nonpolar substance, in water, then what you see is separation. And that's because the oil molecules tend to aggregate with each other. That is, they like to stick together, and because they don't have a positive and negative charge, it's difficult for water to penetrate. So we have this adage in chemistry that like dissolves like. That is, polar molecules like water will dissolve other polar molecules like alcohol, but it will not dissolve unlike molecules like oil. So this is a picture of oil floating or petroleum floating in water. What happens is that the organic chemical, like oil, because it's non-polar, sticks with themselves. Water, on the other hand, undergoes hydrogen bonding. So here's an illustration of water and oil trying to mix. And here's a movie of that same process. So we see when we put nonpolar chemicals with polar chemicals, what happens when you take, for example, an ionic, what makes the difference between an ionic substance versus a covalent substance? Why do some ionic substances dissolve in water, and why will covalent substances also dissolve in water? What makes solubility possible? Well, we've already seen the mechanism by which ionic substances dissolve in water. It's because of the positive-negative interaction with the water molecules. Here you see an example of, again, water orientating itself to the ions in sodium chloride, thus breaking it up and breaking up the lattice. When covalent substances like alcohol, remember, alcohol like ethanol is covalent because it doesn't have any metal in its molecular formula. The reason why it can dissolve in water is because that chemical is polar, that is, it has a positive and negative charge interaction with it, and water can orientate and dissolve that substance. And it does so through something called hydrogen bonding. Here's another example of water dissolving ionic substance. When salt dissolves, it dissolves to a limit and then it stops dissolving. What actually happens is that as some of the ions go into the solution, other ions will go back into the lattice, and we have something called an equilibrium. And so although it looks like nothing's happening at the atomic level, we actually have an exchange process. And an equilibrium is a situation in which the forward and the reverse process are equal in rates, and so it looks like no net change occurs. And this equilibrium is governed based on Le Chatelier's principle, which we will cover more, I believe, in chapter 11. An example of equilibrium is like a traffic in a toll bridge. As 5 cars move in towards the bridge, 5 cars move out of the bridge, and it looks like nothing's moving, but really at close level, the cars are actually moving through. So, what is the difference between ionic versus covalent compounds? Well, ionic substances are what we call electrolyte because they can break into their ions. Covalent compounds don't have metals, and so they don't break into ions, they stay intact, and so because they don't break into ions, they're called non-electrolyte. Substance, when dissolved and break into ions like sodium chloride, are electrolytes. When it stays intact like sugar, they're called non-electrolyte. Electrolytes tend to conduct electricity because, as you see in this picture, the ions can move freely. Strong electrolytes is when the ionic substance break up 100% in water to its ion. Weak electrolytes are when the ionic substance do not break up 100%, and so it's slightly soluble. And of course, non-electrolytes are substances that do not break up and form ions at all, and so they are non-conductors, as shown in that illustration.
We know from various lines of experimental evidence that solid sodium chloride consists of an ordered three-dimensional array of sodium and chloride ions. Solid sodium chloride is not a conductor of electricity. The ions of the ionic lattice are held in place by the strong ionic interactions in the solid, and therefore are not free to move under the influence of the electric field. When sodium chloride is dissolved in water, it forms a solution of separated sodium and chloride ions. The presence of ions in the solution is responsible for the fact that the solution is a conductor of electricity. Substances such as sodium chloride that exist in aqueous solution entirely or nearly entirely as ions are called strong electrolytes. By contrast, an aqueous solution of a non-electrolyte, such as sugar, does not conduct electricity.
So here you saw that one of the characteristics of an electrolyte is that when you put it in water and it dissolves, the ions are free to break up, and so the ions is like a wire in that it can conduct charges. A chemical that is generally covalent in nature, do not break up into ions, do not have that capacity. So what are the factors that affect whether a substance will dissolve or not? Well, we've already looked at the characteristic of the solute and the solvent themselves, whether it's ionic or covalent. But another way to enhance solubility is by temperature factors. In general, for solids and liquid, if you increase the temperature, you move the chemicals faster and they collide harder with each other, which causes the solute to break down and separate more efficiently. And so in general, not always, you increase the solubility when you increase the temperature. On the other hand, if you have a gas like carbonated water and you increase the temperature, what happens is that the gas will pick up that kinetic energy and then it'll escape from that liquid interface, and so you decrease the solubility. What happens is that the gas escapes from the solvent and you have less gas in the solution. So when you increase the temperature for a solution that has a gas solute and say a liquid solvent, you lower the solubility. What are the pressure factors? Well, the pressure factors depends on pushing these chemicals closer together. When you increase the pressure, you force these chemicals to be closer together. Solids and liquids are already close together. They're in contact with each other. So increasing the pressure will not increase the solubility. When you increase the pressure of a solute, it's not going to get closer to the solvent because they're already close. On the other hand, when you have a gas solute and a, say, liquid solvent, when you increase the pressure, you squeeze the gas into the solvent and you increase the solubility. Take, for example, when you compress gas in carbonated water, what they do in the factory is they squeeze that gas into the water and they bottle it. As soon as you open the cap, you decrease the pressure, and what do? You see the gas escaping. You see the solubility decreasing because the pressure is lowered. So what are the principles of solubility? Solutions are homogeneous mixture of two or more substances. The component of a solution are the solute and the solvent, and if water is the solvent, then we have the aqueous solution.
To prepare a solution of known concentration from a solid solute, we must first weigh out an appropriate amount of the solid. For example, to prepare 250 milliliters of a 1 molar solution of copper sulfate, we first weigh out 0.250 moles of copper sulfate. Most commonly, copper sulfate is available as the pentahydrate. The formula mass of copper sulfate pentahydrate is 249.7. We weigh out precisely 1/4 of this mass, 62.4 grams. Note that the weight on the balance is the sum of the paper and copper sulfate. We next transfer the copper sulfate completely to a 250 milliliter volumetric flask. Water is added and the flask swirled to dissolve the solid. Finally, water is added to bring the total volume in the flask to exactly 250 milliliters.
So this section of the lecture notes deal with solution and solution calculation. So the most common way of depicting concentration, at least in chemistry, is called molarity. Molarity. It's the number of moles of the solute. Remember, solute is the minor component in the volume in liters of the solution, which is the solute and the solvent combined. That's why you always have a volumetric flask that measures the combined volume of both the water you add and the solute that you contain. Now in this example, we're going to calculate the concentration of 16 grams of copper sulfate, and the molar mass of copper sulfate is 159.6. So the way to do that is the following. If you have 16 grams of copper sulfate, and we know that the molar mass is 159.6 grams per mole, then we can do this. Let me erase that. Grams copper sulfate. Then we can use something called dimensional analysis. We put this number in the bottom, 159.6 grams, and 1 over 1 mole, because when you have this molar mass, basically means that 159.6 grams equals 1 mole. And so this is how you would illustrate that. So what we see here is if we take 16 grams and divide it by 159.6, that's about the grams will cancel. That'll be about 0.1 moles. Now, the volume that we have in this particular case happens to be 100 milliliters, which is equal to 0.10 liters. So if you have 0.10 moles of copper sulfate and you have 0.10 liters, then what you have is a 1.0 molar solution. And that's what we see here in terms of the calculation. We have a 1.0 solution right here. Now, other ways of expressing concentration are, we already said molarity, but there's also percent mass, or the percentage of solute in the total solution. There's also something called molality, normality, and mole fraction. In this class, we're not even going to bother to look at these types of concentration calculations, but I do want you to know a little bit of how to calculate molarity and mass percent. These are the two most common ways of expressing concentration. Let's take a look at another example. In this particular case, and I'll just talk through this because this will be minimal in terms of your next test, your next quiz, but I do want you to be comfortable using the moles and how to calculate molarity based on the moles. When you have the moles, you can easily convert the moles of your chemical to the mass of that chemical if you know the molar mass of the chemical, because the molar mass or the molecular weight gives you that relationship. If you know that for every 12 grams of a substance you have 1 mole, then you know that if you have 24 grams of that substance you have 12 moles. So the molar mass is the relationship between moles and mass for the solute. Now, if you have information about the solvent, whether it's moles or its mass, and remember the two are related by the molar mass, or the volume, and the mass and the volume of a solvent is related by its density. The density is expressed of mass per unit volume. If you have those, then you can easily calculate percent mass, because percent mass is the mass of the solute divided by the total mass of the solution. You can also calculate molarity, because if you take the moles of the solute and the volume of the solvent or the solution, you can get molarity. And then for the other two concentration units, you don't have to really worry about it in this class. So let's take a look at percent concentration. you guys know what percent means because you use it every day. When you go to the store and they tell you you have 50% off, it basically means that for every dollar you spend, you save 50 cents. Percent really means nothing more than parts per 100. 1% means 1 part in 100. 99% means 99 parts in 100. When you have a concentration expressing percent, you have the amount of solute in the total solution. So, what is a weight percent? Well, that's the weight of the solute divided by the weight of the solution. Remember that the solution is the mass of the solute and the mass of the solvent together times 100. The units is grams over grams times 100, and you express that by the percent sign. Or, if you want to write it out, it's pph. If you have the percent weight volume, then it's the weight of the solute divided by the volume of the solution, generally expressed in milliliters. So it's grams of solute over the total volume of the solution times 100. And if you want the volume concentration percent, then it's the volume of the solute. This would be like a liquid in a liquid, divided by the volume of the total solution times 100. So if you want a percent concentration, then the key here is to multiply each of these ratio by 100. There's another way of expressing concentration by parts, and that's something called ppm and ppb. When you see a concentration expressed in terms of ppm, parts per million, then it's really nothing more than what we just discussed here, except now the multiplier is not 100. The multiplier is 1,000,000 if we're expressing it in parts per million, or 1,000,000,000, 10 to the 9th, if we're expressing it in parts per billion. Now, why do we quote concentration in terms of parts per million and parts per billion? Because when a very, very small concentration can be lethal, or very, very small concentration is important, then a number like 0.000016% seems insignificant. But if instead you don't multiply that ratio by 100, but instead of 1,000,000, then that 0.000016 now becomes 1.6 parts per billion. And 1.6 parts per billion sounds more important than 0.000016%. That's why we express numbers, concentrations that are significant and need to be brought to the attention of the public in ppm or ppb. So, let's take a look at an example. You have 3.5 grams of copper sulfate. It's dissolved in 100 milliliters. Assume that the density of the solution is 1 grams per mil. What is the concentration in percent mass? What we have here actually is more information that you need. What you need to do is you need to realize that you have 3.5 grams of copper sulfate. That's the mass of the solute. And you have 100 milliliters of solution. Well, if the density is for every 1 gram you have 1 mil, then 100 milliliters is actually 100 grams. And so the way to answer this question is you just take 3.5 grams of copper sulfate divided by 100 grams of solution times 100. And what you have is 3.5% mass per mass, because it's mass of the solute over the mass of the solution. And don't forget to multiply by 100. Now let's take a look at a volume percent. And we'll express this in parts per million. if we take 1 drop of alcohol and put it in 1 liter, what is the concentration in percent and what is the concentration in ppm? Well, 1 drop, it takes about 20 drops to make 1 milliliter. So if you take 1 divided by 20, that volume is 0.05 milliliters. So if we know the volume of the solute, 0.05, and we know the volume of the solution, 1 liter, then we just take 0.05 divided by 1,000 milliliters, because remember, 1 liter is 1,000 milliliters, and you multiply that by 100. Well, when you do that math, the concentration in percent is 0.005. If you take that same ratio, 0.05 divided by 1,000, and multiply it by 1,000,000, then what you have is 50 parts per million. Doesn't 50 look more significant than 0.005? That's the reason why we use ppm and ppb. Now, in California, the legal blood alcohol content is 0.08%. 0.08% of a person's blood by volume. How much alcohol in ounce and milliliters is in a person that weighs 160 pounds, which has about 4.7 liters of blood and has a 0.12 blood alcohol level? Calculate that. Well, let's see if we can't do that calculation. We have 0.12% blood alcohol level. We have a person that has 4.7 liters of blood, and the question is the amount of alcohol. When you see this 0.12%, you need to first convert this to something that you understand. Basically means that you have 0.12 milliliters of alcohol in every 100 milliliters of blood solution. So we can use this information to calculate the amount of alcohol in this drunk person. The way we do that is something called dimensional analysis. You see this 4.7 liters? Well, that's 4,700 milliliters. We now take this conversion factor right here, okay, and we say that we have 100 milliliters of blood and we have 0.12 milliliters of alcohol. You can see that the milliliters of blood will cancel, and what we have here is the milliliters of alcohol that this person has. So let's take a look at the calculation. That number comes out to 59 or 5.64 milliliters, or if you use the conversion factor that for every 29.57 milliliters is 1 ounce, that comes out to 0.191 ounce. Let me write that down and let me show you that calculation. We have 29.57 milliliters equals 1 ounce. So what we have here, if we do this math, 4,700 milliliters of blood times 0.12 milliliters of alcohol divided by 100 milliliters of blood, that comes out to 5.64 milliliters of alcohol. Do the math. 4,700 times 0.2 divided by 100. Now, to convert that to ounces, we can do 5.64 milliliters And we know that for every 29.57 milliliters, we have 1 ounce. And if we do that math, we come up with 0.1907 ounce. So that's the math that you have for this particular problem. And that's the answer that you see here. Now, why is this important? Because if you have 0.01 to 0.029 alcohol in your body, BAC, then generally the average individual appears normal. There's subtle effects, and but generally they're normal. If you have 0.03 to 0.059, then you have a mild euphoria feeling. You feel relaxed, you feel joyous, very talkative. You have a decrease in inhibition. Basically have you can muster up the courage to ask a date or to hit on someone, basically. And your concentration is impaired. If you have 0.06 to 0.09, now you're at near the legal limit. Then you have blurred feelings, your disinhibition and extroversion, your reasoning, your depth perception, peripheral vision, you glare recovery are all inhibited. If you got 0.10 to 0.19, you're at the drunk stage now. You overexpression, emotional swing, angers or sadness, boisterous, decrease in libido. Your reflexes, your reaction time, your gross motor control, you stagger, you slur your speech. Those are all impairment. And then you can see what happens when you have even more blood alcohol, more alcohol in your system. You're in a stupor between 0.2 and 0.9, between 0.3 and 0.39. Your central nervous system is depressed, 0.4 to 0.5. You general lack of behavior. You generally you're unconscious. Your breathing is impaired. Your heart rate might be in a crisis. And then over 0.5, you have a high risk of being alcohol poisoned, and you could possibly risk death. And if you want to see how many drinks it takes, this is a chart you could look up. One drink, if you weigh say 120 pounds, then your blood alcohol level is about 0.04. And this is based on the fact that the alcohol content that you have is about one drink has about 0.5 US fluid ounces, and it has about 15 milliliters of alcohol by volume. So look at this chart and see what happens depending on the number of drinks you have. For most people, 2 drinks will already put you over the limit. Remember 0.089. So these are the amount of alcohol that someone can generally drink before they're over the legal limit. Now shark, they have a very acute sense of smell, and they smell blood. So the question is, a shark can smell blood practically several miles away. What is the concentration of 1 drop of blood in a mile cube? Try to do this calculation just to show the relevancy of that concentration. And so if you take 1 drop, which is 0.05 milliliters, and you convert 1 mile cube into milliliters, what you have is 1 mile cube is 4.17 times 10 to the 15 milliliters. If you take 0.05 and divide it by 4.17 and you multiply by 100 or even a billion, that number still looks very small. If you multiply it by 1 trillion, it looks bigger, but still very small. I actually had to look up in the internet something called a quintillion, which is 1 times 10 to the 18th. And now what you have is that concentration of blood in 1 mile cube is 12 parts per quintillion. So the rest of this talks about concentration, calculation. You can go through this or through your books and read about it. Here we have 0.435 grams of potassium permanganate, and it's dissolved in enough water to give 250 mils. How many moles are in 0.4535 grams of potassium permanganate? First calculate the moles and then divide by the volume in liters. To calculate the moles, you need the molar mass of potassium permanganate. This is a flowchart of how to do it. You take 0.435 grams and you divide by the molar mass of potassium permanganate. That gives you 0.00275 moles of potassium permanganate. Then you divide that moles into the liters of the solution. 250 mils is 0.250 liters, and you find out that that concentration is 0.0110 molar. What is the molar concentration of 1 gram of potassium dichromate? I give you the molar mass of potassium dichromate in, again, 0.250 liters of solution. What is the concentration weight volume? The concentration weight volume is 1 gram divided by, in this particular case, 250 milliliters, and you just multiply that by 100. Okay. Here's the calculation for molarity. We take the 1 gram, we divide by 294.2 to get the moles, and then we divide that answer by 0.250 liters. To calculate this, what we have is 1 grams divided by 294.2 grams divided by 0.250 liters, and we get 1.36 times 10 to the negative 2 molar. To calculate the weight volume, what we have is 1 gram divided by 250 mils times 100, and that's 0.400 weight volume percent. When we want to target a concentration, for example, what mass of potassium permanganate is needed to prepare 500 mils of 0.200 molar solution, then what we do is we take the 0.200 moles per liter and we use the 500 milliliters to get the moles in that solution. Here again is a flowchart of how to do that, but basically what you're doing is you're taking the 0.200 moles per liter and you're using that to figure out how many moles in 0.5 liters. So if you know that there are 0.200 moles in 1 liter, how many moles are in 0.5 liters? Well, there's going to be half of that. So you take the 0.5 liters, you multiply it by 0.200 moles per liter, and then you convert the moles to grams using the molar mass. And if you do the calculation correctly, that comes out to 29.4 grams. So if you want to prepare a solution that is 0.200 molar and you want to prepare 500 mils, what you need to do is you need to take 29.4 grams of potassium permanganate, put it in a 500 ml volumetric flask, and then fill that flask after you add the 29.4 grams of potassium permanganate with enough volume so that the total volume is 500 mils. The next section is about dilution. And dilution is taking a concentrated solution and making it less concentrated. That's what dilution means. And generally that means adding more solvent. So if you have a frozen concentrate orange juice, that's too concentrated to drink. What you do is you just take that frozen concentrate in the pitcher and then you add water to it based on the direction. So that frozen concentrate orange juice is now dilute so that you can consume it. Same thing with chemicals. When you have a solution and it has a certain concentration, by adding more solvent like water, the solute hasn't changed. You've just increased the number of solvent, but now the concentration is lowered because there's less solute per the volume. Whenever you calculate dilution, then you want to remember a equation. M1V1, that is the molarity of the solution 1 times the volume of solution 1, is equal to the molarity of the diluted solution times the volume of the diluted solution. Another way of expressing this is C1V1 equals C2V2. Let's take a look at this example. Potassium nitrate, nitric acid HNO3. We want to dilute that. Suppose 10 mils of the 3.4 times 10 to the minus 2 molar nitric acid solution is diluted to 50 mils. What is the new concentration? Well, the original concentration is 3.4 times 10 to the minus 2. The original volume is 10 mils. So that's M1 and V1, or C1 and V1. The new volume is 50 mils. So we just have to plug it into this equation and do the calculation. And in fact, that's what you see. What we have here is the following. We take 10 times 3.4 times 10 to the minus 2 molar and divide it by 50. And when we do that, we get a new concentration of 6.8 times 10 to the minus 3. Let me show you that. So what we have in that problem was that the concentration of nitric acid is 3.4 times 10 to the minus 2 molar. The volume of that solution was 10 milliliters, and we want to prepare a solution that's 50 mils. So our equation is C1V1 equals C2V2. We know what C1 is. We know what V1 is. We know V2. We know V2. We just need to calculate C2. So when we do the algebra, C2 is equal to C1 times V1 divided by V2. That's just simple algebra. So if we plug in the numbers, we get 3.4 times 10 to the minus 2 molar times 10 milliliters divided by 50 milliliters. The milliliters will cancel. The molarity is the unit that you will have, and this number comes out to be 0.4. It becomes 6.8 times 10 to the minus 3 molar. That's the concentration that is seen, that is calculated. And that's what you see here. Here's another example. There is a bottle of 0.5 molar sucrose. So that's the original solution. Give precise direction to your assistants to prepare 250 mils to prepare. That's the new volume of a 0.348 molar sucrose solution. That's the new concentration. So what you have here is you have V1, you have C2 and V2. Calculate, in this particular case, V1. How much of the stock solution do you need to prepare this solution? This is another example. This is a dilution problem. 10 grams of Manganese sulfate is placed in a 1 liter volumetric flask. What volume is necessary to prepare 250 ml of 0.050 solution? Assume the density is 1 gram per ml. So what we have is 10 grams of manganese sulfate and it's placed in a 1 liter container, and we need to know the volume of this solution to prepare 250 milliliters of a 0.050% solution. Let's take a look at that problem. In this particular problem, we have 10 grams of that. What we need to do is we need to figure out what the concentration of this particular chemical is. And what we have here is we need to know the volume 1, because we have the volume that we want to prepare, we have the concentration of what we want to prepare. Again, it goes back to C1V1 equals C2V2. We want to calculate, in this particular case, the volume of this particular chemical. Now 10 grams in 1 liter is nothing more than that right there. So 10 divided by 1000, that's going to give you 1.0%. So we know what the C1 is. All we have to do is calculate V1. V1 is equal to C2 times V2 divided by C1. What we have is 0.050% times 250 milliliters divided by 1.00%. That volume comes out to be 12.50 milliliters. So what we need is, when we put the 10 grams into the 1 liter solution and we fill to the mark with water, then we can draw from that 12.50 milliliters and stick that into a 250 ml flask and fill to the mark with water. And when we do that, that concentration, which is C2, is going to be 0.050%. That's how you would solve that particular problem. So you see right here, take an aliquot, the aliquot is a portion, 12 mils of the 1% solution, and dilute to the mark with 250 mils. So that summarizes chapter 6, at least the solution part of chapter 6. And this right here is a brief summary of the calculations and the concepts that we learn here.